First of all, a big thank you to the organisers for the invitation to speak today. I'm going to be talking about the Galactic Centre, and specifically I'm going to be telling you about a new survey of the Central Molecular Zone called ACES. It's the ALMA CMZ Exploration Survey. And it's an interesting time to give this presentation. It's something that we've been working very, very hard on over the past few years. And as a collaboration, we're kind of in this phase where we're transitioning from what's been a very data-intensive phase to moving towards the science goals of the proposal itself. So it's a new ALMA large program. It was a huge investment of time from the facility, over 1,000 hours of observing time when you factor in the different array configurations, over 100 hours of 12-meter time. And so you should think of this talk as, first of all, a kind of a showcase or an advertisement for the survey itself, but also in keeping with the spirit of the conference, I want to kind of highlight the magnitude and the complexity of the data that we're now dealing with. So before we get there, I wanted to give you a bit of an introduction because I'm aware that perhaps a lot of you are not familiar with, let's say, the geography of the Central Molecular Zone. And I wanted to start with this question here, which is, why do we have a central molecular zone in the first place? And these next few slides were partly inspired by Frederique's talk on Monday, where she was talking about W43 and its important position in the galaxy being located at the bar end. And so it got me thinking that, we have to try to remember that we live inside a galaxy, trying to remember that large-scale context. And this is really important in the context of the Central Molecular Zone. It's a direct consequence of the fact that we live in a barred spiral galaxy. So as with 2/3 of all spiral galaxies in the local universe, the Milky Way hosts a stellar bar. And it's the stellar bar that's actually very effective at driving material from the disk of the galaxy towards the nucleus. So from large scales to small scales, gas following orbital streamlines that become increasingly elliptical as you get towards the inner regions of the galaxy. When those streamlines become more and more compact together, these gas on those streamlines can collide. Angular momentum is distributed outwards and the gas plummets in deeper to within the potential. And the observational manifestation of this is the dust lanes, the bar lanes that we see in these beautiful images of HST images of nearby spiral galaxies. As it makes that journey, it then settles into a second set of orbits that lie deeper within the potential, so-called X2 orbits. And it's this that we actually observe as our central molecular zone. But of course, this isn't our view through the galaxy. We're looking down the barrel of the gun through the plane of the galactic disk. This is Gaia's all-sky view of the galactic plane. And just for reference, many of the star-forming regions that we've heard a lot about over the past week, we can see here. So we can see Orion is over here. We have the Taurus and Perseus regions here. And I'm using this just to highlight one of the challenges that we face when we want to study the Central Molecular Zone. So we have to peer through the entire galactic plane to get towards the center. So in order to do that, we typically go to longer wavelengths. This is Spitzer's view of the Central Molecular Zone. So just for reference, I will probably very lazily switch between CMZ, Central Molecular Zone, Galactic Center. Whenever I do that, this is the region I'm talking about. It's the inner sort of 250 parsecs or so of the Milky Way. Over the next few slides, I'm going to give you a kind of cartography, a multi-wavelength view of the center of the galaxy to kind of highlight some of the regions that I'm going to be talking about throughout the talk. So in each of the images, you'll see a key up here, and that's just to give you some sort of physical intuition as to what the colors are actually representing in each of these images. So just to highlight a couple of features that you can see in this Spitzer image in the mid-infrared. First of all, this is the very center. This is the bottom of the galactic potential. The supermassive black hole at the very center of the galaxy, Sagittarius A star, exists within this region. The bright thing that you're actually seeing here is the nuclear star cluster. Right? It's 10 million solar masses of stellar material that kind of enshrouds the black hole at the very center of the galaxy. The other two bright regions that you can see here are the famous star clusters in the CMZ, the arches and the quintuplet. These are examples of young massive clusters. So 10 to the 4 solar masses of material, sort of half-light radii of about a parsec or so, and ages of a few million years or so. The The other thing that you can see here are these dark regions. You can think about these directly analogously to the Gaia image that I showed you on the previous slide. So these are the dense, the cold molecular clouds that are actually obscuring the background starlight here in the mid-infrared. These are archetypal infrared dark clouds. And the best example of that in this region is this guy here, known as the brick, because of how much of the background mid-infrared it's actually extinguishing. So in order to see these clouds in emission at these temperatures, we fold in longer wavelengths again. This is now Herschel's view of the galactic center. So you can see these clouds begin to show up in emission. We also have bright regions like this. This is actually the Sagittarius B2 cloud. Not only is this incredibly chemically rich, as we've just learned, but it's also one of the most massive molecular clouds in the galaxy, 1 million solar masses of material. And in the present day, it accounts for half of all the star formation activity that's going on right now in this entire region. So this thing is forming stars like crazy. Going to even longer wavelengths, we can fold in, this is the Meerkat observations in the radio. We begin to see emergent protoclusters, so H2 regions, as high mass stars begin to ignite. This is the Sagittarius B1 region here. And then we also capture the end of the stellar life cycle in these supernova remnants that we see here as well. So this is just to kind of give you a feeling for the region, but it's also to highlight the fact that within this sort of relatively small area on the sky, about 250 parsecs or so, we have all these different phases, evolutionary phases of the star formation process. Everything from very dense quiescent molecular clouds like the brick, which show very little signatures of active star formation, all the way through to fully fledged star clusters like the arches and the quintuplet. And yet, there are still open questions. So when I talk about the CMZ, I like to frame my talks around this result. It was a result published by Steve Longmore in 2013. And it provides a lot of context in this particular talk because of what it inspired following it. And the result goes as follows. The present day global star formation rate at the center of the galaxy is about 10 to 100 times lower than what we would expect. Now I'm going to put my imaginary helmet on right now because we're going to talk about dense gas. So what do we mean when we say dense gas? This has been quite controversial. I don't need to introduce this plot, but it's the Gauss-Solomon relation, looking at the relationship between the mass of dense gas and the star formation rate in different environments. Okay, so these can be full galaxies as shown on here, but also resolved regions within individual galaxies as well. It's been quite controversial over the week. So we had Fred, which showed this particular plot. I think it was maybe the Schmidt-Kennicut relationship, actually. But actually a really interesting idea of following the evolution of starburst regions through these star formation relations. Mario argued that HCN, in this particular case, may not necessarily be tracing the dense gas. We had Sophia from the extragalactic perspective that was telling us that the ratio between HCN and CO, a proxy for the dense gas fraction, doesn't necessarily trace with surface density. Antonio had a bit more optimism, I think, kind of glass half full, potentially tracing the HCN was, at least to some extent, tracing the N2H+. And Miriam was telling us that, again, we may be overestimating the mass of dense gas. Philippe had a rather provocative view, which was, does this tell us anything about star formation whatsoever? Okay, so I'm going to go through this a bit like a politician, but I quite, just to paraphrase Jens's talk, I think the important thing here is what this x-axis actually means, and what we think it means may not necessarily be tracing what we're actually looking at. In the context of my previous slide, in terms of expectation, the Milky Way, if we judge it by the characterization of dense gas from the perspective of extragalactic observations, so just in terms of the luminosity of HCN, or if we judge it by the classification of dense gas from local clouds, i.e. above the mass of dense gas above some column density threshold, in either case, it sits below this relationship. Okay, and this is where this inference that it seems to be underperforming when it comes to forming stars comes from. So without getting into the details of why that's the case, I think what that has actually done is it's inspired a couple of big questions that people have tried to address over the past 10 years or so. One is whether or not we happen to be observing the center of the galaxy at a low point currently in its star formation history. And I think that we now believe that to be true. We think that star formation in the center of the galaxy happens in quite a bursty way. So the arches, the quintuplet clusters, are a good example of this. Both kind of formed a few million years ago. We also, if we look at the nuclear stellar disk and look at the actual star formation of the nuclear stellar disk, we can see that the star formation rate that would be predicted in that region would be factors of several higher than it is today. Okay, so we think that this is not a constant thing, and it's probably closely related to the larger scale picture, right? That flow of material providing fresh material to the center of the galaxy. The other side of this is the work that's been done on the small scales. So in terms of the physical conditions in the gas, are they actually inhibiting star formation in some way? So we see elevated gas densities, increased turbulence, high magnetic field strengths, high cosmic ionization rates, high gas temperatures, all relative to what we would see in nearby molecular clouds. And as we saw from Antoine's talk a couple of days ago, if you think about the sort of the density PDF, the idea is that potentially you're shifting the goalposts required to form stars. So the kind of the picture that I'm trying to build here in the way that I actually see the Milky Way CMZ now is kind of like an ecosystem. We have the small scale physics of the interstellar medium, but then we also have this larger scale picture of the galactic potential that's actually supplying fresh material. And in fact, this fresh material we think may be one of the sources of the drivers of turbulence in the gas, which impacts then the small scale physics. So from a Milky Way perspective, the central molecular zone offers a way in which we can kind of stress test our understanding of star formation. So do our models for star formation that apply in perhaps local molecular clouds, are they even relevant under these extreme conditions? From the extragalactic perspective, it remains the only galactic center that we can actually resolve the physics of star formation from 100 parsec scales down to the scales of individually forming protostars. And so it's a way in which we can get sub-beam information relative to nearby galaxy centers. And this is something that I just want to advertise very quickly. I'm now working as part of Ava Shinera's team at the MPIA. And what we're doing here, this is a gallery of nearby galaxy centers observed with ALMA as part of the FANG's eCMZ project. So 10 to 20 parsec scale resolution observations of nearby galaxy centers. So how can we connect our own galaxy center to these nearby galaxy centers? Okay, ACES. We have a few people in the audience. It's a big team, but we've got Jaime and Miriam here today, and Ash may be online as well. But I wanted to, so before I get onto ACES, I wanted to kind of focus on the work that's come before us, not necessarily in terms of the science, but in terms of the approach. So here we see, again, the image of the galactic center. I'm overlaying the kind of the footprints of various observational programs targeting individual regions within the CMZ. So these are ALMA Band 3 observations pre-ACES, the CM Zoom survey, which was a legacy survey with the SMA led by Cara Battersby, and then the KARMA survey as well. The point here is that we wanted to get the entire region. We want to understand this multi-scale picture of star formation. But what we had, at least before ACES, was that it was like trying to navigate Paris with only the information of individual landmarks throughout the city, but without the map of the city itself. Right? Lots of the city is happening in between these kind of famous objects, focusing on the brick or Sagittarius B2. With ACES, we wanted to do something different. Right? We wanted to map the entire region. And we wanted to do it in a homogeneous way. A lot of these surveys that came before were very heterogeneous, whether that's in terms of resolution, the spectral setup, the spectral resolution, the sensitivity. And these things all matter when you're trying to make comparisons between regions and build an overall picture. So our goal was to build a complete and multi-scale picture of the physical processes that are shaping this central region down to the scales of individually forming stars. The strategy was to create a uniform survey, Band 3 with ALMA. Band 3 because it offered us a primary beam that meant that we could actually observe the entire region in a kind of quote-unquote sensible amount of time. In molecular lines and in dust continuum, and down to a resolution of 0.05 parsecs. The goals were to, first of all, try and determine the physical mechanisms that are actually driving the mass flows, the energy cycles, not only as a function of location in the CMZ, but also as a function of scale. We want to try and disentangle the three-dimensional geometry of the system. And that's really difficult because we're looking along the line of sight and we have to rely on kinematic traces in order to help us break some of those degeneracies. Related to that is to determine whether or not there are preferred locations for star formation in galactic nuclei in general, not just our galactic center. Think back to Frederick's talk and the kind of the formation at W43 at the end of the bar. In the galactic center, we have the flow of material flowing from large scales, colliding with the gas in the central molecular zone, driving up the density and leading to protocluster formation as that gas orbits the center of the galaxy. And then finally, to look and see whether these models for star formation actually hold in environments like this. This was the way we did it. It ended up being the largest contiguous mosaic ever produced by ALMA. It's about 5,000 band 3 pointings, covering the entire region in this patchwork quilt-like thing. If you've got kids, it looks a bit like Elmer the elephant to me. And we did this across a range of different gas traces that were informed from the surveys that came before us. Okay, so HNCO, which is a bit of a strange molecule in the context of the CMZ specifically, it's typically thought of as a tracer of low velocity shocks, but we kind of see it tracing the structure in the dense gas as well. HCO+, CS, HC3N, etc. We have shock gas tracers, so SIO and HNCO. Ionized gas to trace the kind of the young star forming regions, and then dust in the continuum as well. So the data. This is really to give you a showcase of the data, and I actually just want to highlight, I'm living vicariously through other people here and the hard work of other people in the data reduction team. So I want to highlight Ashley Barnes, who may be online right now, Jaime Pineda as part of the data reduction team, and Alvaro, I think I saw online the other day as well. But this is our data reduction team led by Adam Ginsberg, Dan Walker, and Ash Barnes. This is ACE's view of the galactic center. This was part of a press release that ESO very kindly put together for us. You might have seen a flurry of ACE's papers appear on the archive the other day as part of our first data release. And what we have here is a combination of these different traces that we have. So shock gas tracers and dense gas tracers as well. What I want to highlight here is the complexity in the data that we have. Right, incredibly filamentary, incredibly detailed, and I'll show you some zoom-ins of this data as well. But if we just to isolate one of the lines here, this is the HNCO data cube. For reference, this is a single line, single data cube, and it's about 0.5 terabyte in size. And we have many lines. So we're kind of in a regime where the data volume is really kind of hindering us, and I've been really interested to hear a lot of your work in the audience and the kind of techniques that we can maybe use to actually start to analyze data sets of this magnitude. So this is our high spectral resolution band going down to about 0.25 kilometers per second. A couple more highlights. We have here, this is a zoom in. Again, this is focusing on the HNCO line. We see here the Sagittarius A clouds. These are the clouds that appear closest in projection to Sagittarius A star at the very center. Of course, the brick here as well. And this, I wanted to highlight, this was the very first ACES paper. It's a bubble just south of Sagittarius B2. And this was published by Mari in this paper here. Mari was actually an undergraduate when she published this paper. She came to work with Ash and Katerina Immer, ESO, as part of a summer project, and I just wanted to highlight her work in this. This is to give you a sense of the improvement. This is the data set that I actually started to work on when I was a postdoc going to work with Steve Longmore in 2016. This was the data set that was given to me. Single dish MOPR observations of the HNCO line. And then you can see the kind of the improvement looking at these individual regions that I've just zoomed in on. In terms of the science, we've started to scratch the surface, I would say, of this immense data set. This is some work from Cara Battersby. The contrast isn't showing up great here, but this is looking at different populations of extended structures, filamentary structures within the region. And she sort of identified at least two, but we need to do this in a uniform way, populations of filaments. So large scale extended structures, sort of 10, 20, 30 parsec scale structures that appear to be tracing the actual orbital structure. And this is some work by Yoshiaki Sofue, who's tried to put this into a three-dimensional context and provide us with a top-down view of the actual orbital structure. And then a second population, very small, hyperlinear in many cases, and narrow, which are largely pervasive throughout the entire HNCO map. This is some work by Miriam in the audience here today, which is actually looking at the different chemical signatures. So not only are these filaments different in terms of their physical properties and dynamical properties in some sense as well, but also showing some chemical differences here if you look at the ratio of HNCO to many of the other lines that we have in the data set. The kinematics are, of course, incredibly complex. This was a pilot study of Sagittarius B2 region where, again, like the talk that just came before me, we've done a kind of a Gaussian decomposition of the data. Almost every single sightline that we see in our HNCO data cube has multiple velocity components. It's incredibly complicated. This is just translating this Gaussian decomposition back into 3D position velocity space with velocity on the vertical axis here. So each data point here is an individual Gaussian showing the location and this velocity centroid, where the color is giving you a feel for the amplitude of those individual components as well. And if we do that, and this is an analysis that we have to try and do in this region because of the complexity, but if we do that, we start to see things that are very interesting. This is some work of my PhD student, Rajita, who's based at Liverpool John Moores University, but she's spending a year at the CFA at Harvard. And she's been analyzing this region. This is one of the clouds in the dust ridge for which we have complementary JWST observations. And when you break the line up into these individual Gaussian components, we begin to see these incredibly narrow features in the data, about 0.5 kilometer per second wide. For years in our proposals, when we were asking for data on the CMZ, we always would say things like, we don't need the best spectral resolution because the lines are super broad, the turbulence is super high in this region. This is telling us this was actually wrong. Once we get down to these scales, we're starting to see the scales. Cast your mind back to Jaime's talk today, where we actually start to see the energy dissipating in this gas, and we see these incredibly narrow features. So in analogy to low mass star forming regions, where we see these cores, where we see the energy, the turbulent energy in the gas dissipate, potentially this is telling us the regions of incipient star formation in the central molecular zone. So this will be my final slide. So talking about the challenge ahead that we're going to face. We've kind of now made the map of the city, but the problem is now we have to read it and understand it. So a couple of the major challenges that we're facing is the scale of the data. So our lines are hundreds of gigabytes, up to 0.5 terabyte in size. We have many, many lines. Complexity, both in terms of the physical complexity of the distribution of the gas across the plane of the sky, but also the kinematic complexity with multiple velocity components, and the diversity as well. So some regions are more complicated than others. It's not just a case of having uniformly narrow lines or uniformly broad lines. We see a mix across the entire region. So I want to put a positive spin on that and say this is, even though that challenge is potentially quite intimidating, it's actually a really exciting time to have this data set come to completion and science ready. And it is the first time that we're going to be able to analyze this entire region in a systematic and a statistical way. So it's kind of watch this space. And with that, I will stop talking and thank you for your attention.
Thank you. Questions?
Hi, Johnny. Very nice talk. I have 2 questions. The first one may be a little bit naive, but I'll just proceed with it. So you said that basically when you decompose the velocity in the CMZ of the Milky Way, that you actually, what was previously thought that it's just super broad line is actually consisting of several narrow features. Did I get that correct?
Yes, you've got that correct. At least that's what we said in our proposals.
Okay.
No, that's not true. Okay, so in general, if you were to take, for example, the line width size relationship, if you were to compare the line width size relationship in the disk and in the center, there's a vertical offset. right? But there's definitely more turbulent energy in the gas on a fixed spatial scale in the central molecular zone. We're now arriving, if you kind of follow that power law down, we're now arriving in a regime where that is not true anymore. And so in some regions, I'm not saying in all regions, and this is something that we have to do more diligently across the entire environment, we're starting to see these regions where we see incredibly narrow lines, and it's just not something we've ever seen before.
And this actually comes to my very first question, which is basically, do you think that this is actually what might be happening in other galaxies? Because we know that when we map CO emission or HCN emission in nearby galaxies, that also the line width in the center is quite larger than outside. Could that also be the case, but it's just impossible to resolve because we are limited by the spectral resolution?
So the short answer to that is there's going to be a paper arriving in your inbox very shortly about that. The longer answer for everyone else is yes, exactly. So particularly if we look at high mass barred spiral galaxies, this is the idea that we see much higher line widths and much higher surface densities towards the central regions. If we actually take that spectral information and decompose that data, what we're seeing is a reduction in the velocity dispersion and the surface density. The importance there is if you were to plot this in a kind of velocity dispersion versus surface density diagram, in which you can infer the dynamical state of the gas, so kind of a bit like the higher-keto relationship, you observe a distortion in that plane. So what happens is you reduce, you sort of dampen the difference between disks and centers in terms of velocity dispersion and surface density. But then if you think about the relationship in something like the virial parameter, which is sigma squared over sigma, you amplify the difference in the dynamical difference between the two. And so what we see is that the individual components as we go to high mass barred spiral galaxies don't look gravitationally bound, but because of the self-gravity of the gas, right? The background potential is still important, but yes.
And another question, because there is an alchemy survey of 253, also targeting the CMZ. I forgot the frequency coverage, but do you have any similar features that you mapped with ACES? And can you maybe do some comparison in terms of is the Milky Way CMZ any special, or is it more 253s? I mean, we know that 253 is a starburst, but just...
Yeah, so they're very different in that sense. So 253 being a starburst compared to the Milky Way Center is kind of a WIMP in that regard. I would say the comparison between alchemy and the CMZ has more come from the single dish observations, right? With ACES, we're getting down to core scales, and so there's quite a difference there. So in terms of the direct comparison, in terms of the physical structure, I'm not sure what we can do, but there's also extremely high resolution observations of 253 outside of that. I would have to look. I don't know off the top of my head. I think alchemy it by design traces a broader range of species than ACES does specifically, but I can't recall the details.
Okay. Maybe a quick question about the data processing point, because you've shown very impressive reconstruction results. So I'm wondering what is the strategy behind? Is it something similar to the classical iterative clean method? Is it something else?
Yeah. So I'll just bring this up. So in terms of the imaging, each of these fields were imaged individually. And there was a range of different techniques that were actually explored. So in terms of the classical approach of joint deconvolution of the 12-meter and 7-meter data, and then feathering the total power, for example, in terms of using the total power as a model with the joint deconvolution. And then the final approach, which is kind of feathering, imaging individually, the fields individually, and then feathering those. The final one is what we chose. It's not necessarily what all people would choose, but there was a balance between processing time and kind of fidelity, ultimately, in the quality of the data. That said, obviously, what we did do was take individual fields and process them in different ways and did a comparison in complicated fields. And the result of that was that we felt confident that the feathering approach wasn't going to lose us too much in terms of the quality of the end product. But that was the approach we took in the end. Jaime, I don't know whether you wanted to add anything to that, but
that's not each one thing, but it's each file set.
Yes, yeah, sorry. Just for clarity. So each element of this patchwork quilt was, and then it was stitched together afterwards.
Great. So we are in time. So there was another question.
I was just curious. Are these the only lines you have? I mean, where is the ACN and the N2H plus?
Pardon,
why did you pick those lines to start? Have you reduced ACN and N2H plus? I mean, that's what we want.
So we we don't have N2H plus, actually. So the line selection came from much of the work that came before. And so we wanted a kind of spread. So a major driver, okay, how to phrase this. The spectral setup was divided into three. We wanted a high spectral resolution band, right? Because we wanted to target these narrow lines. And so HNCO, which was a faithful tracer of the kind of the gas structure, both on large scales with the single dish moth predator, but also on small scales with ALMA as well, was the obvious choice there. And then in terms of what we could get in addition in that band, it was the HCO plus. We then had an intermediate kind of spectral resolution band, about 1 kilometer per second resolution, where we wanted a range of diverse tracers. And then we had a lower spectral resolution band, which is kind of our continuum band, but also allowed low brightness detections of individual lines. It just so happens that N2H plus and HCN are not included in that particular setup. Next proposal. Pardon? But the isotopologues are of HCN.
It's going to be hard to compare this data with Galactic.
As a direct one-to-one across the full thing? Yes, potentially, but I mean, we can do that from a different perspective if we focus on the actual surface density calculation, if we can make that claim. Yeah. But as a direct luminosity of HCN across the region, yeah.